All right, students, let me try another video solution here. Here is chapter 22, number 7. And here they're talking about refrigerators, but keep in mind that refrigerators, heat pumps, and of course the heat engine itself, probably the easier of the three to understand, are really all kind of doing the same thing. A refrigerator is kind of acting like an engine in reverse. But anyways, let's just read it here. It says a refrigerator has a coefficient of performance of 3. And the reason we call it coefficient of performance as opposed to an efficiency is because if this is kind of the model of a refrigerator, I'm not trying to draw really anything about the mechanics and the freon inside of the refrigerator and the compressor and the evaporator. But if this is the refrigerator, here's the idea. That you got to put a little bit of energy or work in. This would be usually say if this is a kitchen refrigerator, this would be the plug. And so some electricity comes into the plug. And the idea then is it would take energy out of the cold compartment and throw it out or force it out into the hot environment. That'd be the room. So that'd be the kitchen, and inside here, this would be the freezer. So we're taking energy out of the freezer or refrigerator and putting it into the kitchen. That's why perhaps you've ever stood near your refrigerator near the bottom. Especially if you're barefooted, you'll feel that heat coming out of the bottom. It usually kind of blows out on the bottom onto the kitchen floor there, and so a little bit of warmth coming out because you're cooling something down. And I think this one was talking about freezing ice or something. So a refrigerator has a coefficient of performance of 3. Yeah, the ice tray compartment is at negative, so over here we've got negative 20 degrees Celsius, and the room is at 22 degrees Celsius. So we're trying to go against nature in the sense that we're trying to take energy from this cold environment, because maybe you put water in there, and you want to take energy out of the water and make it into ice. So you got to take the energy out, and you got to do something with it, and you got to put it into the room. And that's the opposite effect of what it would do on its own, and so we've got to put work into it. Obviously, this area taking heat out is a decrease in entropy, but this is an increase in entropy. So that's another good question about entropy, but let's not go there. That's not what this problem is about. Okay, so let's see. It says room. The refrigerator can convert 30 grams of water at 22 degrees Celsius and to 30 grams of ice at negative 20 degrees Celsius each minute. Okay, what is the input power? So they're talking about how much power is going into the motor in order for this to happen. And they've given us some help here by telling us how quickly it freezes water. So let's talk about this. Let's say we have our 30 grams. And it says here it can go 30 grams per 1 minute, which is 60 seconds. Okay, but let's talk about how much energy would come out of that. And so there we got to go back a couple of chapters, because we would have, I would call Q1, which would be the cooling down of water. So maybe I'll put cooling water. Then once we cool the water, we have to then freeze it together. And so maybe I'll just say, okay, this is the whole idea then of our freezer. So number 2. Okay. Maybe I better do that. Okay, and then once we then freeze the water into solid ice, we now have to cool the solid form which would bring it down from 0 degrees to the negative 20 degrees Celsius here. All right, so the cooling of the water would be an MC delta T. The freezing would be the latent heat of fusion. And then the cooling down again would be an MC delta T, although we would be cooling down ice. And so ice has a different specific heat than water. Okay, so let me put in some numbers here. Here's our 30 grams of, starting with water. And there is 4.186 joules for every gram for each degree it cools down. And it's going to cool down 22 degrees. It's going to start at the 22 and eventually get to 0. Of course, it's going to cool even more than that later, but it's not water anymore. So that's the water part of it cooling down. Then we've got the 30 grams of water, which is now at 0 degrees, and then it is going to begin to turn into ice. And it requires 333 joules for each gram to be removed. And then we can, again, this third piece, we've got the 30 grams now, and I need to kind of look that up. It's roughly a half, and so 4.186 divided by 2 is going to be about a 2.093 joules per gram for each degree C. And to give myself quite enough room, but we're going to cool it down another 20 degrees. That would be from 0 degrees down to 20. Now, I should check that number, and I'm also kind of wondering about that number, if I'm really remembering right here. And so let me check. Let's see, 333. Okay, good. 2.090, not a 3. Well, okay, like I said, it's really close to half. Okay, so those seem like good numbers here. And so let me just figure out the energy that needs to come out of the water, and that's what these three factors are. So I've got 30 times 4.186 times 22. Add to that 30 times 333. Whoops, 333. Add to that 30 times 2.090 times 20. And it looks like we need 14,007 joules. Grams would cancel, degrees Celsius. And so we're talking about joules coming out of this, well, what once was water and now is an ice cube, and a cold ice cube at that. Okay, so if we look at then the power coming out of it, it would be this 14,007 joules, and they said this could do it, I believe they said per minute. Now, let me go back to the question. Number 7, each minute, yeah. So this is during a 60-second time interval. So during 60 seconds. So 233.4 joules per second, or watts, is coming out of the ice compartment and going into the kitchen, I guess, in this case, assuming the refrigerator is in the kitchen. Okay, now the beauty of a refrigerator, and the reason we call it the coefficient of performance, let me come back up here. I started to mentioning the coefficient of performance, is because the amount of energy it can actually removed can actually be quite a bit more than the work required to put in. It's kind of a leveraging effect. That's why we don't want to call it an efficiency. You know, like heat engines, we call it efficiency because you can't get more out than you put in. That's a violation of conservation of energy. But here you can actually get more out than you put in, not because you're violating any kind of principle here, but you're taking advantage of some kind of leverage, some kind of situation that's already there. Probably an easy example of this is an avalanche. You know, if you were on the edge of the snowbank, you could probably throw a rock. And so that small amount of energy then triggers something that then releases all the energy that's already stored. And this massive avalanche falls from the top of the mountain down into the valley. And there's this huge release of energy. All that energy didn't come from you throwing the rock. The rock was the trigger mechanism to release it. And so you release a lot more energy than you put into it. And that's the ideas of these heat pumps. And so in this case, they say the factor is a 3. And that means then for every 1 joule you put in, you release 3. And so it's got this efficiency, not efficiency. It's hard for me to, I always want to say efficiency, but it's coefficient of performance of 3. Because it's not really an efficiency. Although people always use it incorrectly and call it efficiency, as I just almost did. It's not an efficiency. That would be a bad use of mathematics to call it an efficiency. But yet we do. Because we're really talking about the performance of it. And so our natural reaction is to talk about how efficient it is. But it's a coefficient of performance. Okay, so with that in mind, let's come back down to here. Because we know the coefficient of performance is 3. If I take the heat coming out of the cold environment and divide it by time, and the work going into the engine divided it by time, see, I've got to multiply top and bottom by time. This is the power coming out of cold area. And then this is the power from the wall. How much electrical power do we have to do? And so that's what they're after here. So power from the wall would actually be this power coming out of the cold environment divided by a factor of 3. That's the whole coefficient of performance. So the energy coming out is 233 joules. If we divide that by 3, we're looking at 77.8 watts. So the electric motor itself is only consuming 77.8 watts. And in the process, it's using a leverage system, if you will, and in this case, the compression and expansion of Freon. And it's drawing more out. It's kind of like saying, hey, follow me. I'm going to do this. And so the motor does actually very little, and then 3 times that comes following along behind it. Like I said, kind of my avalanche example. It just kind of follows suit. Or maybe the Judas goat, if you're into farming and cutting meat, you know, they send the goat up the ramp, and all the cows follow, and each one gets slaughtered. That's a pretty gory example. Let's not do that one. But it just takes one goat, and then 100 cattle follow along, and so it doesn't take much effort, and then they all follow into the slaughterhouse. Okay, so with that in mind, I'll say let's call this one quits.